Hi there, Mr. Sutton bringing you a lesson on recursion. In this one, we will be finding the nth term in a recursive sequence and writing recursive definitions for sequences. For a warm-up on this one, in the famous Fibonacci sequence, each term is calculated by adding the last two terms together. If the first two terms of the sequence are 0 and 1, find the next 5 terms. Pause the video and do that now. Alright, so we've got 0 and 1, that adds up to 1. 1 plus 1 is 2, 1 plus 2 is 3, and 2 plus 3 is 5. And are we done? Oh, nope, wait, one more. 3 plus 5 is 8. And we could keep going on and on forever. So for the next question here, what is a formula for the nth term of this sequence? Give up? So this is a tough one to come up with a formula for. Part of the problem is how we define the term formula. What you were probably trying to do is to come up with what is called an explicit definition. This is just a normal function that you just plug n into and get the nth term. There is actually an explicit formula for the nth term of a Fibonacci sequence, and here it is. This only approximates the nth term, but you can see this is pretty crazy, and this is not something that you would be able to come up with on your own in a small amount of time at least, or to memorize really. There is another kind of formula that we're going to talk about today, and this is called a recursive definition. A recursive definition, you start with an initial condition, an initial term or two, and then there's a recursive rule that helps you find the next term. So for example, in the Fibonacci sequence, your initial condition would be your first two terms, 0 and 1. We would call that A1 and A2. And the recursive definition, AN or TN, whichever you prefer, you're just going to take the last two terms, we'll call them AN minus 1, that's the last term, the term right before this one, and AN minus 2, that's two terms before this one, and add them together. If we write the rule like this, it's a much simpler rule to write. We're going to talk more about these recursive definitions now. We're going to do some work with some more recursive sequences. For this one, we have a recursive sequence where the rule is take the last term and add 7, and our initial condition is 33. So for your first part on this, find the first 4 terms, and then see if you can move beyond that and find the 10th term. Alright, let's see how you did on part 1. So for using a recursive sequence, you just have to start with your initial condition and apply the recursive rule, and then just keep doing it on each new answer. So for example, to find the second term, we have to take term 1, that would be 2 minus 1, A2 minus 1, and add 7 to it. So 33 plus 7 gives us 40. To find the third term in the sequence, we just need A2 plus 7. So that would just be 40 plus 7, or 47. A4, we're just going to find 47 plus 7 again, and so on and so forth. How about the 10th term of this one? So for going several terms beyond where you currently are, you need to figure out, what am I doing over and over again, and is there a shorter way of doing it? Well, here we're just adding 7 over and over again. Instead of adding 7 a bunch of times, what's a shortcut for addition? Why, multiplication. So we know that we're just taking our first term and adding 7 a certain number of times. If I want to get from the first term to the 10th term, I have to add 7 9 times. So I could just do the first term plus 7 times 9. So 7 times 9, that is 63, plus another 33 gives us 96. Here's another recursive rule example. Pause the video and try this one out. Alright, so for this one, we're multiplying the last term by 3, and we're starting with negative 4. So term number 2, that'll be negative 4 times 3, which is negative 12. For the next term, we just multiply negative 12 by 3, so negative 36. And for the next one, we just multiply negative 36 by 3. So that'll be negative 108. Now, we could keep doing this to get the 10th term, or, well, what's a shortcut for multiplying by the same thing over and over again? Repeated multiplication is just exponents. So if you want to multiply by 3 9 times after that first term, you just need to do 3 to the 9th power. And I'll use the calculator for that, which will give me negative 78,732. Here's another example for you to try. This one's a little bit weird, but give it a shot. The key to this one is realizing that n is the index number. So if you want the second term, you're just taking the last answer, which is our initial condition of 8, and adding the index of 2, because 2 is your current index number of the term that you want. And that, of course, gives us 10. Now, to get the third number, we need to do this last answer, 10 plus 3, because, again, that's the current index, giving us 13. How about the next one? Oh, well, that's just 13 plus 4, which is 17. We could keep doing this, but how about if we want the 10th term? So just to visualize what's going on, for the 10th term, we would just be starting with our initial condition, and for our second term, we added 2. To get the third term, whatever answer that gave us, we added 3, and then 4, and then so on up until the 10th term. But what are we actually adding here? Well, this is an arithmetic series. So I guess you could plug all these into your calculator, but what if this was give them asking for us for the 1,000th term instead of the 10th term, right? So what would be a shorter way of doing this in the long run? Well, arithmetic series, you have to take the first and the last term, average them together, and then multiply it by the number of terms. So we've really got 8 plus, if we're adding an arithmetic series, 2 plus 10 over 2, all that times 9, because there's 9 more terms that we need here. So that's going to be, let's see, 12 over 2 is 6, times 9 is 54, plus 8 gives us 62. For example 4, we're going to do the same kind of thing we did with example 3, except instead of adding n to the last term, now we are multiplying it by the last term. Pause the video and see how far you can get with these two parts. All right, so now we're going to be doing the initial condition of 3 times 2 for the second term. That's 6. Then we'll have to multiply that by the next index of 3, which gives us 18. That gets multiplied by the next index of 4, which gives us 72. And if we want to keep doing that to get the 10th term on this one, well, how can we keep multiplying by an increasingly higher number? Let's just write out what we would be doing and see if we can find a pattern for it. So we've got our initial condition of 3 times the second index of 2 times the 3 for the next index. Then we would do times 4 times 5 times all of them up to 10. So how can we do all of this on the calculator without writing it all out? Again, it's not that bad when you're just going up to 10, but what if this was 100 or 72 or something crazy like that? So a shortcut for multiplying by all of the whole numbers less than 10 up to 10 on your calculator, and you always do this when you're multiplying by the index, you're going to use the factorial button. Let me show you that on the calculator. And just to write out what you're going to be looking for in the calculator, we're going to want to express this as 3 times 10 factorial. So let's take a look. So I've got my 3, open a parentheses to multiply, I've got the 10, and the factorial button, you have to go to the math menu, and if you arrow over to PRB, that's for probability, because factorials are used in probability, it's the fourth option here, this little exclamation mark. So go down to that, press enter, and this is now multiplying 3 by 1 times 2 times 3 times 4, all the numbers up to 10. And enter. Gives us a very large number. That's 10,886,400. So this gets used a whole lot in probability, especially when you're dealing with permutations and combinations, but it's also useful here. Now that you've gotten some practice with using recursive rules, we're going to go backwards and write a recursive formula for a sequence. So first thing you should do on this, and this is the easier step, is write down the initial term. That's just the first term. So we would say for this one, A1 equals -7. Next, we have to write a recursive rule to get each next term. And when you're doing this, you have to look at the sequence and ask yourself, what's happening to get from one term to the next? Is it addition or multiplication? Is it changing by a constant, or is it changing by the term's index? Because remember, we can add or multiply by the actual index of each term as well. In this case, we're going down by 10 for each next number in the sequence. So since we're subtracting 10 from the last term, we can write an equals the last term. We express that again with an minus 1 minus 7 to subtract 10. Here's another one for you to write a recursive formula for. Pause the video and see how far you can get. All right, So we're starting with an initial condition of -1. That's our A1. Now how do we get from A1 to A2? So there's a lot of different ways to get from -1 to -2. What I would recommend doing is, give yourself a little hypothesis of how to do it, and then see if that rule applies going for the rest of the terms here. So one way to do this would just be to subtract 1. But if I subtract 1 from -2, do I get -6? I do not. So we're not just subtracting the same number each time. Okay, well, another option is maybe we're multiplying by the same number each time. To get from -1 to -2, I would have to multiply this by 2. If I multiply -2 by 2, does that give me -6? Nope, it would give me -4. So multiplying by the same thing each time also isn't going to work. Another option would be adding or subtracting the index number. Well, the index number for this second term is 2. We can't really use a 2 to get from -1 to -2. How about multiplying by the index number? -1 times 2 again gives us -2. To get the third term, we would have to multiply this by 3. Oh, to get the fourth term, we would have to multiply this by 4. To get the fifth term, we'd multiply this by 5. Well, by George, I think we've got it. So we're multiplying by the index number each time. So then we could write AN equals AN minus 1 times N, or just N times AN minus 1. Now, how did I figure this out? Well, you were here when we did this a second ago. We just looked through a bunch of different possibilities until one of them fit all the terms. So sometimes you just have to try things out and then test it to see if it works. To finish off this lesson, I just wanted to talk briefly about how recursion is actually used and practiced in real life. So very often when you're using a recursive function, we don't actually start at the bottom and work our way up. More typically what happens is if, for example, you want to know the fifth term, you ask the computer, okay, what's the fifth term? And the computer says, oh, well, the fifth term is going to be 5 times the fourth term. Oh, wait, what's the fourth term? Well, that's going to be 4 times the third term. Oh, wait, what's the third term? And it just keeps working its way down until it gets to this initial condition. At that point, it can actually start answering all the questions that it just kind of put on hold because it didn't have enough information about those lower terms. Now, another use of recursion is for sorting things. If you want to ask, for example, what's the highest number in this list of numbers, often how a computer will do that is it'll be like, okay, the highest number is going to be whatever's higher between this half of the numbers and this half of the numbers. Oh, what's the highest number between this half of the numbers? Well, that'll be the highest number between this half of this half. And I mean, it just works its way down, divides and conquers, and then you start getting answers to work your way back up. That's how recursion functions normally. So, until next time, this is Mr. Sutton signing off.